Aloha everyone. My name is Audrey Lynn. I'm a junior at Iolani School and taking honors independent research. And today I will be presenting my project titled Looking Ahead, Building Predictive Models of Electricity and Oil Consumption in Hawaii to Inform Public Policy. So my work begins with a fundamental question. How can a young person like myself create meaningful systemic change, specifically within community-based movements that one believes in and wants to see reform? For me, I seek to fight for the environment as I see climate change as the greatest threat our planet currently faces. Without the right to vote nor access to huge sums of money, what power does a 17-year-old really have? Well, for me, the answer was public policy. Through writing testimony, organizing community-based events, lobbying over Zoom or in the Capitol, I found purpose in advocating for environmental policies that held real political power. So in 2022, I co-founded the Climate Future Forum, whose mantra is for youth by youth. We focus on intergenerational change and lobby for interdisciplinary solutions that span from carbon cashback to subsidies for renewable energy, from farm-to-school programs to just transition task forces. This image is from when I testified for Senator Gabbard's public climate information briefing at the state capitol. However, throughout this process, I also encountered an issue, a disconnect between policy and tangible research. I realized that both legislators and community members cannot make any effective change without truly understanding the scope of the issue through scientific research. So that leads me to my background. As an island with its unique behaviors, diverse cultures, significant influence from native traditions, and tropical climate, Hawaii is unique to say the least. Furthermore, the state's electricity policies and renewable portfolio standards are the most ambitious in the United States, which seek 100% of net electricity generation to be renewable by 2045. However, according to a study conducted by Energy Information Administration, ground transportation, which makes up 25% of petroleum use in Hawaii, must reduce by 70% to reach the state's Clean Energy Initiative goals. In 2022, 472 million gallons of petroleum were used for ground transportation, which, according to the Aloha Plus Challenge, needs major improvement. As you can see on the figure above, the light blue line shows the trend of our state petroleum use per year in the transportation sector. This is starkly contrasted to our target use, which is seen in the dashed lavender line. So as you can see right now, the state of Hawaii is in a crucial period for energy conservation and resource management. And to successfully achieve this goal, it's similar to what I mentioned earlier. Utility companies, community members, and legislators all need accurate predictions and tools to make a successful transition to renewable energy while meeting the demands of our population. Therefore, building strong and local predictive models is really important, especially since past literature has stressed the implementation of community-based local carbon management studies, since the effectiveness of solutions are nuanced based on their geographic location. In other words, the findings from a study conducted with data from the mainland would not be as applicable to Hawaii, since our climate and culture is so different. Therefore, the geographic location and granularity of my project makes my research truly novel. So that leads me to the progression of my research questions that I sought to answer with my project. First, based on previous data and available literature, in the state of Hawaii, how does energy usage change over time? Second, how can we best model this data in a predictive and accessible manner? And third, can we make a website that makes policy more accessible to the public? Beginning with my first question, I sought to examine how energy usage changes over time. To do this, I wanted to find the data available for energy consumption to understand the trends over time in Hawaii. I pulled monthly electricity consumption data from the Hawaii Department of Business, Economic Development, and Tourism Data Warehouse. The monthly electricity consumption over time for Hawaii is graphed in the blue figure above. My total sample size was 210 values, and each data point was composed of a value, monthly electricity consumption, and a date. Perhaps surprisingly to some, the state's electricity consumption is actually decreasing due to our reliance on new technologies like LED lighting, changes in GDP, and warmer weather conditions. This leads me to my next question of how can we best model this data in a predictive and accessible manner? To begin, I reviewed previous literature that predicted electricity consumption using both artificial intelligence and conventional methods. In a study conducted by Dr. Matt Doubt, a hybrid combination or an aggregate sum of predictions from both artificial intelligence and conventional methods was shown to produce the most accurate predictions. So that is what I intended to do with the following three models. My first model was the linear regression, which is used to predict the value of a variable based on the value of another variable. It is a simple, standard, and accessible predictive model, and it's widely used in trend forecasting, like predicting costs or weather patterns. To make this first model, I split the dataset that I mentioned earlier in half, which resulted in the training set, which was fed directly into the model, and the testing set, which was deemed the quote, accurate prediction, and compared against the results of the forecasting model. This 50-50 split was chosen based on previous similar studies, such as a study conducted in Brazil by Dr. Da Silva in 2022. Developed with the training set, the R-squared value for my linear regression was 0.51, which presents a significant correlation for social science. I then extrapolated the trend line of the training set to January 2023, and the percent error was 11%. In addition, the linear regression model seen above reaffirmed something I already knew, that electricity consumption has a non-stationary mean and a downward sloping trend. So the next model that I created was an ARIMA model, which stands for the Autoregressive Integrated Moving Average. This model was coded in Python, and according to the available literature, ARIMA models are best utilized for time series models, which represent some non-stationary data over time. This description is applicable to my dataset, where electricity consumption values change over time. First, we had to visualize the series patterns by using a method called seasonal decomposition. It is important to note that the ARIMA model only processes stationary data, where trend and seasonality have to be minimized. Trend refers to how the data changes over time. Seen in the upper line graph, there is a clear downward trend, and seasonality refers to those cycles that happen again and again. Here you can see that electricity consumption tends to peak in warm summer months, which is a pattern that repeats annually. To do this, I used a method called differencing, which is the process of subtracting different variations of the dataset from each other to minimize trend and seasonality. For example, one variation of the dataset I used was the exponential moving average that results in the weighted average of the last n consumption values, where the weighting decreases exponentially with each previous month. In other words, recent values hold a greater impact on predictions than old ones. To check when the data was truly stationary, I used the augmented Dickey-Fuller test until I found that the data's test statistics were greater than its critical values. At that point, when the data was truly stationary, I used Python to fit my data to the ARIMA model. Ultimately, the ARIMA model resulted in the graph below, which shows the range of predicted electricity consumption values to the 95% confidence interval until 2047, when our electricity consumption will be approximately 3.72 thousand kilowatt hours. So referring back to my guiding question, for my third model, I wanted to enhance the accessibility of my model. Therefore, I decided to use barrels of oil as my unit for electricity consumption because a barrel is more tangible for the average citizen. So starting off with a bit of background, according to the Hawaii State Energy Office, the amount of fuel imported into Hawaii exceeds the amount of any other product imported into the state. I decided to craft a model that projected the total barrels of oil that an individual's lifestyle contributed to, specifically in the transportation and residential realms. Coded in over 200 lines of Shiny code in R language package, I created this adapted slider model. Each model has a quote threshold value, and using the threshold logic function, the model will tell the user whether their behavior is below or above average. The two slider models were based on the above equations, which calculate for the output unit in barrels of oil. Some data I had to collect included average vehicle speed from the Honolulu Traffic Commission, the CO2 factor for Oahu from the EPA, and the conversion from kilograms of CO2 to barrels of oil from the EIA. The data that the user would input themselves includes their commute time and car model for the transportation slider, and for the residential slider, they would input their energy bill and HECO's residential energy rate. This leads me to my last question. Can we make a website that makes policy more accessible to the public? Therefore, I created the Looking Ahead webpage, which features an interactive application with the slider models I just discussed. The application and webpage are coded in R and HTML, and the site also features a legislative bill tracker to inform community members about the current status of climate-related bills that I hope can be a tool for like-minded citizens who want to stay engaged in the democratic process. In all, I was able to visualize our state's energy usage over time, create 3 models of energy consumption, and make my website accessible to the public. I also want to note that today it is easy to be overwhelmed by the abundance of news articles that discuss the extinction of various species and the global destruction caused by natural disasters. However, though young people cannot yet vote nor hold office, they can still make huge waves of change, whether through scientific research or active civic engagement. To continue this project, future research should examine more types of models, like the recurrent neural network, the deep neural network, and the optimized gray model. Also, future research should implement more variables like GDP, carbon sequestration technology, and vehicle registration fees into the same models to test whether increased complexity actually results in increased accuracy. I also plan on publishing my website and sending it to various community members and legislators, along with a survey to see how useful the website is and how it can be changed to make it more accessible. My piece of advice for future students taking independent research next year is to formulate project ideas in advance and keep an open line of communication with your mentors and peers. I also wanted to note that this year, my research didn't go exactly how I wanted it to go. I wanted to acknowledge that there were some difficulties and obstacles that led to this point, but ultimately, I want to encourage others to take this course because it really pushes you to try new things. Before this class, I had never ever considered coding within a remote realm of things that I could and wanted to do, but with Mr. Hill's help, that happened and actually became an integral part of my project. And that leads me to my acknowledgements. A huge mahalo to Dr. Chan, Dr. Bernstein, Dr. Kaufman, Mr. Hill, and of course, my period 3 research friends. Thank you.